Hi everybody. Today we are going through the combined loads chapter that I gave you on a handout from Mr. Bailey. And this is posted to our Moodle page. So we've covered sort of the second half of this handout first, in that we talked about Moore's circle, and now which was in the second half of chapter 16 from the handout. And now we're going to go back and talk about combined loads. So the good news about combined loads is that there's nothing here that is new to you. What we're doing in this chapter is we're taking a lot of ideas that we've already come up with in the previous chapters in the textbook and bringing them all together. So there's a very important concept which is called the principle of superposition, which means that if you have two normal forces, for example, or normal stresses, pardon me, you can add them together arithmetically if they're in the same direction. So basically, if you have a tension and compression, the absolute value of the combined sigma will be smaller. If you have two tensions, the absolute value of the combined sigma will be larger, and so forth. And the same is true for tension. So if you look at this page, this is the first page of the handout, you'll see that we have sigma for an axial load as P over A, and torsion for a, in other words, well, I guess it would be the torsion would be the torque, that we have a shearing stress in the amount of TC over J. And then for a bending load, which is not pure bending, but rather is a bending load that causes not only a sigma in the amount of MC over I, but also causes that VQ over IT. So basically what we have is that there are four sources of sigma and tau, and we can add the sigmas together arithmetically on the same axis, and we can add torsion together arithmetically on the same plane. So this is where it becomes very important that we keep the direction of tau negative or positive consistently, even though it doesn't have the same physical meaning as tension and compression, for example. It's just a direction, but the direction becomes extremely important because we need to know whether the absolute value of tau will add or subtract. So if we have combined loads, that just means that we have perhaps a P and a T and maybe a V that creates a moment or something like that. And so what we do is we can add these together, remembering that we can just add the sigmas and add the taus as long as we keep the signs straight, and that will come up with the total that represents a state of stress. So how do we do that? Okay, the first thing is, as always, to draw a free body diagram. We need to be able to determine the moment and the shearing force and the axial force, and if there's a torque, we also need to determine that. Now, all of these can add together as well, and one place that this becomes apparent is when we have done shear moment diagrams in the past. When we do shear moment diagrams, we have different values of V and different values of M across a structural member. Another one is if we have some sort of a combine of a load where in the past we've had like a column of two different diameters that's extruded from a ceiling, and we have a load at the end of the entire apparatus, and then we have a load maybe where the two pieces of the apparatus are welded together, and so that the P in one section is different than the P in the other. And with torsion, we have cases where we had a drive shaft, for example, that had a torque exerted at one end and then maybe an intermediate torque exerted, so that the torques on different parts are different. So that's why we need to do a free body diagram. We need to solve for the external reaction. We need to get the reaction A, reaction at B, whatever our end points, our supports are. And then we need to redraw the free body diagram with the external loads applied. Now this is exactly like what we did for the first step of the VM diagrams. Okay, then we cut the body at the point of interest. We do that cutaway and draw a free body diagram of the cut. That's because we need to get the internal reactions. Once again, this is just like we did for VM diagrams. And then we identify and solve for unknown torques, moments, shears, and axial loads. All right, so what we want to do then is to calculate sigma and tau, keeping in mind the sign convention is very important for each one of these loads. So sigma total is going to be a sum of sigma from the axial load plus sigma from the bending. Tau total is going to be tau from the bending, which is the VQ over IT, plus tau from the torsional load. Once again, keeping in mind that we have to be careful of our sign convention. And so these 8 steps result in us being able to find the state of stress, in other words, sigma total and tau total at any point on a structural member. So example 6.1 talks about this idea. We want to find the state of stress at point A and point B for a particular figure, which is right here. We draw a stress block, and then we talk about what's going on with sigma and tau at those 2 points. All right, now first of all, I want to say when Mr. Bailey draws something like this, the triangle here at D represents a fixed support. The circle at E represents a rolling support. So that allows it not to get into a bind. And we're talking about a cut 4 feet from the end right here, which is to the right of the 150-pound applied load. So we're in between here and here. So we have a fixed support, a rolling support, and then on this cut 4 feet in, we want to find sigma and tau at point A and at point B. All right, so the first thing we do is a free body diagram. Since we have a 300-pound applied load here, there's going to be a reactionary load here. Then we have 150 pounds. We know that the sum of the reaction at D and the reaction at E will be 150, but in order to determine the amount of each, we're going to have to do a moment diagram, or summation moments about some point is equal to 0. And doing that, we find that the reaction at D, the vertical reaction is 120 pounds, and the vertical reaction at E is 30 pounds. Okay, so then we draw our cut. So if you look, there he's moving from this side to this side. So in other words, Mr. Bailey starts on the right and cuts on the left, which is the opposite of what I usually do, but there's no reason not to do it. One good reason to do it is it eliminates the occurrence of that applied 150-pound load in the free body diagram of the cut face, but it's actually going to be just about the same thing. But so if you wish to cut the other way, it's fine, but this will work as well. All right, so we do all that stuff, we get our moments, and then we can compute sigma due to, if we look at this, we have a sigma on the axial load, so that's going to be a P over A. Then we have an MC over I. If we look at this cut face, and we look at where we're looking at point A from the moment is going to be in compression. Point B from the moment is going to be in tension. So when we find P over A, it's going to add to point B, but point A's moment is going to subtract from the P over A load. So we found both of those things. We find sigma equals MC over I, or My over I is the way that our book termed it, because at B, of course, we are going to be C because it's the maximum distance from the neutral axis, but A is just halfway between. So we have a sigma due to the bending moment, and then we also have the P over A, which is just 300 over the cross-sectional area. And then we do the same for shear. Now here all we have is a VQ over IT. There's not a torque. And once again, we can't really do a torque unless it's a circle, and we can't really do VQ over IT unless it's a rectangle or an I-beam. So there would not really be a case where both of them would occur in the same problem in this class. But there's going to be several cases where you have both an MC over I, or an My over I, and a P over A sigma. All right, so then we found tau total, and we've got sigma total. And so we can draw a stress block for point A, where we have our sigma in the x direction, which is in compression, and we have a tau in the xy plane. Then we can do the same thing for point B. The only difference being that, like I said, at point B, I think they've subscripted this incorrectly, but yeah, the subscripts are a little wonky here, but basically what they're talking about is sigma from bending, not at point B. They're talking about sigma from bending, and then sigma A is sigma from axial. It's confusing because the points are A and B, but they're talking about what's causing sigma in each case. So then tau, once again, is going to be, why is it 0? Well, because if it's at the outermost fiber, VQ over ITQ is 0, so tau is equal to 0. So this is a complete stress block of point B. All right, so that is the topic for combined loads. The next problem, example 16.2, talks about what happens if you have a torque. Now in this case, it looks like we have some applied loads. We have a 300 Newton load, and we have a 1200 Newton meter torque. So we have something else a little bit going on here, but it's sort of the same, it's exactly the same idea, where we sum everything going on the cut face, and then in this case we have this torque. Now we're also going to have a VQ over IT here. So this is something we didn't really talk about in our class. I told you that the only shapes that we would use for specific VQ over ITs would be either a rectangle or an I-beam. So here we also have a Q and an I for a circle or a semicircle. I don't think I'm really going to put anything like that on the exam, but I just want you to be aware of it, and the values are given in this problem, so you can see that. All right, but it's the same idea. We just add them together. If they're in the same direction, subtract one from the other. If they're in opposite direction, come up with a sigma total and a tau total. All right, so that is the only lecture, the final lecture from this handout. I'm just scrolling through to make sure that I haven't left anything out that I would like to tell you before you get started on the homework. But I think we're good. I may make a choice to spend a little bit of time talking about the possibility of having a circular shaft if we have a combined torque. But if we do, it's going to be very simple geometries. Now remember, we can't really use a torque if we have a rectangular cross-section, because we need that extraordinarily high degree of symmetry in order for our equations to work. So that's not going to be a concern, but could we possibly have a circular shaft that also has not just a tau from a torque, but a tau from a vertical load as well? I think that will be for discussion for our final lecture on this chapter. Okay, so that's the end of chapter 16, because the last part of chapter 16, where we start talking about Moore's circle, was covered on the previous two lectures. So you're now prepared to do your homework. I will curate the problems a little bit after I decide what I'm going to do about circular structural members. So have a great day.